In this lecture we'll answer two questions. The first question, we find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. In the second question, we find out there on this circle that is described by trapezoid ABCD. So we start with the first question. In the drawing, we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. In addition, we know that OS equals to SB, and this is square PQSO that is located inside this semicircle. Again, our task is to find out the size of this angle AMQ that is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles in any square are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. In addition, we know that all the sides of any square are equal to each other. So in square PQOS, side OS equals to the opposite side QS. So I can write down that QS equals to OS. But it is given us the question that OS equals to SB, OS equals to SB. And from this equation, QS equals to OS equals to SB, we derive that QS equals to SB. QS equals to SB. In the next step, we will do a construction, that is to say, we will join points B and Q together by a straight line. And we will extend the straight line BQ by straight line until it touches the circle. And we will define the touching point of the extended line segment BQ with this circle. This point is point N. By doing this construction, we get the right angle QSB. This is the right angle QSB. We have the rule that in front of equal sides in the triangle there are equal angles. So if we look to the right angles QSB, actually we have to prove that the triangle QSB is a right angle. AB is the diameter of this semicircle. So write it down. AB is the diameter of the semicircle. AB is the diameter of the semicircle. It is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is equals to 90 degrees in its size, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as y, then the size of this angle must be also equal to y, because they are equal to each other according to the rules dimension. We know that the sum of the angles in any triangle is equal to 180 degrees. Therefore, the sum of the angles in this right triangle QSB must be equal to 180 degrees. So which angles have the right triangle QSB? Y plus y, it is 2y plus 90 degrees. In total, it must be equal to 180 degrees, according to the rule that the sum of the angles in a triangle is equal to 180 degrees. Repeat again, in the right triangle QSB, the sum of the angles must be equal to 180 degrees. That is to say, 2y plus 90 degrees equals to 180 degrees. Here we will subtract 90 degrees from this equation, and we get that two y equals to 180 degrees plus 90 degrees is 90 degrees. 2y equals to 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle y equals to 90 degrees over 2 is 45 degrees. So actually, this is the missing angle y, that equals to 45 degrees in its size. Likewise, this is also the missing angle y, that equals to 45 degrees in its size. We joined points B and Q together by a side line, and then we extended the side line BQ by a side line, and we got line segment BN. When we extend the side line by a side line, the result must be a straight line. Therefore, BN is a straight line. So if we focus on the left side of the straight line BN, it's point Q. Here the sum of the angles must be equal to 180 degrees according to rule 3. That said that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have the left side of the straight line BN at point Q? We have this angle that is 45 degrees in size, plus this angle is equal to 90 degrees in its size, that is a right angle, plus this missing angle, that is actual angle NQP. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Repeat again. The sum of the angles in the lower side of the straight line NB at point Q must be equal to 180 degrees. That is to say, 45 degrees plus 90 degrees plus the missing angle NQP. In total, it must be equal to 180 degrees according to rule 3. 45 degrees plus 90 degrees, it is 135 degrees. So 135 degrees plus the missing angle NQP. In total, they must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and we get that the missing angle NQP is equal to 180 degrees minus 135 degrees is 45 degrees. So the missing angle NQP equals to 45 degrees in its size. This is the missing angle NQP. This is the missing angle NQP. Is equal to 45 degrees in its size. In the next step, we join points N and M together by a straight line. And we join points N and A together by a straight line. By joining points N and A together, we created triangle A and B. This is triangle A and B that subtend on AB, that is the diameter of this semicircle, and according to rule 7, any triangle that subtend on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. So I repeat quickly rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtend on the diameter of the circle. This is chord AB. And therefore, peripheral angle ACB, according to this rule 7, must be equal to 90 degrees in its size because it's subtend on the diameter of the circle. So we can implement rule 7 in our drawing. In our drawing, we have peripheral angle A and B that subtend on AB and chord AB, that is the diameter of the semicircle, and therefore peripheral angle A and B must be equal to 90 degrees in its size according to rule 7. So we focus on the right triangle, triangle A and B. This is the right triangle A and B. In the right triangle A and B, this angle equals to 45 degrees in size. This is the right angle plus this missing angle. In total, the sum of those three angles must be equal to 180 degrees according to the rule that the sum of the angles in the triangle is equal to 180 degrees. And therefore, this third missing angle must be equal to 45 degrees in size. We have the rule that in front of equal angles in the triangle, there are equal sides. So in the right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. That is to say, side AN is equal to side NB. Therefore, triangle A and B is an isosceles triangle. So triangle A and B is simultaneously the right triangle is also an isosceles triangle because side AN equals to side ANB. So right now, we should find out that the right triangle ANB is also an isosceles triangle. The base of the isosceles triangle, triangle AB is AB. Again, AB is the base of the isosceles triangle, triangle AB. So right now, actually, AB is the base of the isosceles triangle, triangle A and B. So here we can implement rule 24. according to Rule 24, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have triangle ABC. This is an isosceles triangle. Why triangle ABC is an isosceles triangle? Because side AB equals to side AC. The base of the isosceles triangle ABC is BC. And according to this rule 24, the perpendicular AO to the base BC bisect the base BC. So AO is a perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 24, the perpendicular AO bisects the base BC. If the perpendicular AO bisects the base BC, it means that it divides it into two halves. Each half must be equal to BC over 2. So BO equals to BC over 2. This is the first half. And the second half OC also equals to BC over 2. And the first half BO, of course, equals to the second half OC. So BO equals to OC equals to BC over 2. So we can actually implement Rule 24 in our drawing. Well, because in our drawing, we have the isosceles triangle, triangle A and B. In the isosceles triangle, triangle A and B, the perpendicular from point M to the base AB bisects the base AB. That is to say, according to Rule 24, of course. That is to say, it divides the base AB to two halves. Each half must be equal to AB over 2. So the first half is AB over 2, and the second half is also AB over 2. But AB is also the diameter of the semicircle. So if the radius of this semicircle is R, then the diameter must be equal to 2R. So AB equals to 2R. This is the diameter of the semicircle, this equals to 2R. And the perpendicular from point N bisects the base AB. The base AB equals to 2R. So each half must be equal to 2R over 2, that is R. So the first half is the radius of the semicircle, that is equals to R. And the second half is also the radius of the semicircle, that is equals to R. But the question is where the perpendicular from point N will touch the base AB. The perpendicular from point N bisects the base AB according to Rule 24. That is to say, the perpendicular N must touch the base AB at its midpoint, because it bisects the base AB. That is to say, it must touch the base AB at its midpoint. What is the midpoint of AB? The midpoint of AB is the midpoint of the diameter, because AB is the diameter. The midpoint of any diameter is at the center of the circle or the semicircle. So the midpoint of the diameter AB must be its point O, that is the center of the semicircle. Therefore, the perpendicular from point N will touch AB, its point O, that is the center of this semicircle, according to what is given as a question. So first of all, NO is perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So the perpendicular NO bisects the base AB. The first half is AO, that is the radius of this circle, and the second half OB is also the radius of this circle, of the semicircle, that is R. And point O is the midpoint of AB, that is also the center of this semicircle. We know that the opposite sides of a square are parallel to each other. So in square PQOS, side PQ is parallel to the opposite side OS. And we have the rule that corresponding angles between parallel lines are equal to each other. Those two angles are defined as corresponding angles, and are located between the parallel lines PQ and OS. And therefore, those two corresponding angles are equal to each other. But this angle is 90 degrees, and therefore this angle must be also equal to 90 degrees in its size. according to the rule that I mentioned. This is triangle NBA or ABN. Triangle NBN, triangle ABN equals to 45 degrees in its size, and triangle ABN subset or called AN. Likewise, this is triangle AMN, triangle AMN subset on the same code called AN, exactly like triangle ABN. They are both subset on the same code called AN. And therefore, they must be equal to each other with their sizes according to Rule 16. According to Rule 16, if two or more triangles subset on the same code, then they must be equal to each other and their sizes. Repeat quickly on Rule 16. According to Rule 16, triangles that subset on the same code are equal to each other. In the drawing, we have a circle. This is triangle AOB that subset of code AB. Likewise, we have the other triangle ACB that is subset on the same code called AB. And because of the fact that those two triangles subset on the same code called AB, they must be equal to each other in their sizes. That is to say, angle AOB equals to angle ACB, or alpha equals to beta. So if two or more triangles subset on the same code, they must be equal to each other in their sizes. We can implement Rule 16 in our drawing. Why? Because in our drawing, those two triangles ABN and AMN, they subset on the same code called AN, and therefore they must be equal to each other in their sizes. But the size of triangle ABN is 45 degrees, and therefore the size of triangle AMN that subset on the same code called AN must be also equal to 45 degrees in its size. According to Rule 16, of course. Those triangles are both equal to 45 degrees in their sizes, and the subset on the same base NP. This is angle PQN. Is equals to 45 degrees in size, and it's subset on the base NP. Likewise, this is angle NMP. This is also equals to 45 degrees in size, and it's subset on the same base NP. And because of the fact that those two angles are both equal to 45 degrees, and then subset on the same base NP, they fit to a circle. That is to say, they can be inscribed by a circle. According to the rule that I mentioned 1 minute ago, if you have two triangles that subset on the same chord, then they must be equal to each other and their sizes. So we actually have here, this is triangle PQN, this goes to 45 degrees in size, and this is triangle PMN, this is also equals to 45 degrees in its size, and they are both subset on the same chord called PN, and therefore they are equal to each other in their sizes. That is to say, they are both equal to 45 degrees. Okay? And therefore, if you have two angles that are equal to each other in their sizes and then subset on the same base, they are angles that can be fit in a circle. That is to say, you can inscribe them by a circle, and it will obey to Rule 16 that triangle that subset on the same chord called NP must be equal to each other in their sizes. And we see that each angle equals to 45 degrees in size, and therefore they are equal to each other, exactly according to Rule 16. So in the next step, I'll prove that quadrilateral NMPQ, this is quadrilateral NMQP, it is a cyclic quadrilateral. That is to say, it can be inscribed by circle, it can be blocked by circle. So first of all, what is a quadrilateral that is inscribed by circle? The red quadrilateral ABCD is inscribed by this circle. Why the red quadrilateral ABCD is inscribed by this circle? Because of the fact that all of its four vertices, that is to say A, B, C, and D, they are all located on the circle. And therefore this quadrilateral ABCD is inscribed by this circle. That is to say, it is blocked by this circle. So only if all the four vertices of a quadrilateral lie on the circle, then it is inscribed by this circle. So this is quadrilateral ABCD that is inscribed by this circle. So we have to prove that quadrilateral NMQP, this quadrilateral, is inscribed by circle. That is to say, it can be blocked by circle. So first of all, I'll copy, that is to say, all the three vertices of quadrilateral NMQP must be located on a circle that blocks it. That is to say, vertex N, vertex M, and vertex Q, and vertex P of quadrilateral NMQP, they are all must be located on a circle that blocks it. So first of all, I copied angle NQP, that is equal to 45 degrees in size, and angle NQP is inside triangle NQP. So I copied triangle NQP in a new page. This is triangle NQP, and this is angle NQP, is equal to 45 degrees in its size. We have the rule that says that all the angles in the world, all the triangles in the world can be inscribed by circle. Again, all the triangles in the world can be inscribed by circle, and therefore this is triangle NQP that can be inscribed by circle. So that is to say, we can block this triangle NQP by a circle. So I block this triangle NQP by this circle. And this is angle NQP, triangle NQP, that is equal to 45 degrees in size. Angle NQP subtend on chord NP. Again, angle NQP subtend on chord NP. What is the meaning of triangle NQP that is inscribed by a circle? It means that all the three vertices of the triangle lie on the circle. You can see that vertex N, vertex P, and vertex Q, they all lie on this circle that is inscribed triangle NQP. Again, triangle NQP, in triangle NQP we have this angle NQP, this is equal to 45 degrees in size, and peripheral angle NQP subtend on chord NP. Again, peripheral angle NQP subtend on chord NP. So we have here, this is peripheral angle NQP that subtend on chord NP. The size of peripheral angle NQP is 45 degrees and it subtend on chord NP. Likewise, we have peripheral angle NMP. It is also subtend on the same chord called NP, and it is equal to 45 degrees in its size. Okay. So now here we have other angles that are located outside this circle that subtend on the same chord called NP. This is angle NLP. Angle NLP subtend on chord NP. Again, angle NLP subtend on chord NP, and it is located outside this circle. It's point L. Again, angle NLP is located outside this circle. But the size of angle NLP is 39 degrees. So you can even try to draw another angles that are located outside this circle. All the angles that you draw that are outside this circle and they are located, they are subtended on chord AP will be less than 45 degrees. Like this angle, NLP, that is located outside this circle, and it is equal to 39 degrees in its size. It's subtend on chord NP, and because of the fact that it is located outside this circle, it is less than 45 degrees. It is equal to 39 degrees in its size. Likewise, this is angle NOP, the red angle NOP, that is subtend on the same chord NP, but angle NOP is equal to 85 degrees in its size. We can try and draw another angles that are located inside this circle, and they subtend on the same chord NP. They'll be greater than 45 degrees. So in conclusion, we can say that all the angles that are located outside this circle and line chord NP will be less than 45 degrees, while all the angles that are located inside this circle and line chord NP will be bigger than 45 degrees. Like this angle NOP that is located inside this circle, and it's subtend on chord NP, is equal to 85 degrees in its size. So all the angles that are located inside this circle and subtend on chord NP, they will be greater than 45 degrees. So we can say that only the angles that are located on the circle itself and the all subtend on chord AP will be equal to 45 degrees in their sizes. Like this angle NMP that is located on the circle and subtended on chord NP, it is equal to 45 degrees in its size. Likewise, this is angle NQP that is located on the circle itself and subtend on chord NP, and it is also equal to 45 degrees in its size. Therefore, we can conclude that only the angles that are located on the circle itself will be equal to 45 degrees in their sizes. So the angles that subtend on NP, all the angles that subtend on NP, if we want that they will be equal to 45 degrees in their sizes, they must be located on the circle itself. Therefore, we have this is angle NQP that is equal to 45 degrees in its size, and it's subtend on chord NP. So if we rotate peripheral angle NQP and we'll keep the size of 45 degrees, will not change the size of the angle, we just rotate the vertex along the circle on axis NP. NP will not move. We create infinite angles that are all equal to 45 degrees in their sizes, and they are all located on chord NP, because chord NP is not moving. We just move the vertex along this circle. So we create infinite angles that they are all subtended on chord NP, and each of them will be equal to 45 degrees in their size, because we will not change the size of the angles. We just rotate it like this without changing the size of the angle. So we get infinite angles that all of them, each of them is equal to 45 degrees in its size, and they are all subtend on chord PN. One of those two angles will be angle PMN, that is equal to 45 degrees in its size, and it is also subtend on chord PN. And this is angle PMN. This is angle P. This is angle PMN. Repeat again. This is angle PMN. Angle PMN. Angle PMN equals to 45 degrees in its size, and it's subtend on chord PN. Likewise, angle PQN also equals to 45 degrees in its size, and it's subtend on chord PN. So we can do by rotating peripheral angle PQN along this circle without changing the size of this angle, that is 45 degrees. We created peripheral angle PMN that is equal to 45 degrees in its size, and it's subtend on the same chord called PN. So in the next step, we join points M and Q together by straight line. By doing all those constructions, we created quadrilateral NMQP. It is the same quadrilateral NMQP. So we actually succeeded to block quadrilateral NMQP by circle. Why quadrilateral NMQP is inscribed by this circle? Because of the fact that all of its 4 vertices, that is to say vertex N, vertex M, vertex Q, and vertex P, they are all located on this circle. Therefore, quadrilateral NMQP is inscribed by this circle, or quadrilateral NMQP is blocked by this circle. So we succeeded to prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, it can be inscribed by circle, or it can be blocked by circle, because this circle blocks quadrilateral PNQN. Or this circle, this quadrilateral PNQN is inscribed by this circle. So we can write down in conclusion that quadrilateral PNQN is inscribed by circle. Quadrilateral PNQN is a cyclic quadrilateral. That is to say, it can be inscribed by circle, it can be blocked by circle. So we have already proved that quadrilateral NMQP, it can be inscribed by a circle. It is a cyclic quadrilateral. So we will block this quadrilateral NMQP by a circle. So the red circle blocks quadrilateral NMQP. Why the red circle blocks quadrilateral NMQP? Because of the fact that all the 4 vertices of quadrilateral NMQP lie on the red circle. This is the vertex N, this is the vertex M, this is the vertex Q, and this is the vertex P of quadrilateral NMQP. All the 4 vertices lie on the red circle, and therefore quadrilateral NMQP is inscribed by the red circle. And we have the rule that says that the sum of the 2 opposite angles in a cyclic quadrilateral is equal to 180 degrees. Repeat again. The sum of the 2 opposite angles in a cyclic quadrilateral is equal to 180 degrees in its size. Those are the 2 opposite angles of quadrilateral NMQP. And according to the rule that I presented to you, the sum of those 2 opposite angles must be equal to 180 degrees. This is angle NPQ, that is the right angle, plus the opposite angle NMQ. In total, they must be equal to 180 degrees according to the rule that I presented to you. So angle NPQ is quadrilateral NMQP. Plus the opposite angle, that is the angle NMQ. The opposite angle of quadrilateral NMQP. But again, I should found out that in a cyclic quadrilateral PMQN, the opposite angles are equal to 180 degrees. The sum of the opposite angles is equal to 180 degrees. That is to say, angle NPQ plus the opposite angle NMQ, in total must be equal to 180 degrees. Angle NPQ, this is angle NPQ, that is the right angle, plus this is angle NMQ. Angle NMQ in total equals to 45 degrees plus x. So in total, the sum of those two opposite angles are equal in total to 180 degrees, according to the rule that I presented to you. 90 degrees plus 45 degrees is 135 degrees. So 135 degrees plus the missing angle x, that is the angle that we are looking for in this question. In total, they must be equal to 180 degrees. Here we subtract 135 degrees from the equation, and we get that the missing angle x, that is the angle that we are looking for in this question, it is equal to 180 degrees minus 135 degrees, that is 45 degrees. So she found out that the missing angle x, that is also equal to angle AMQ, is equal to 45 degrees in its size. The missing angle AMQ is equal to x is equal to 45 degrees in its size. And that is the answer to the first question. In the next step, I present to you the second question of this lecture, and the answer of the second question. Our task in the second question is to find out the area of this circle that is inscribed by trapezoid ABCD. So first of all, again our test. The second question is to find out the area of this circle that is described by this trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB. Therefore, quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. In trapezoid ABCD, the two parallel sides, that is to say DC and AB, are defined as the bases of trapezoid ABCD. So if we define the length of the base DC as A and the length of the base AB as B, then the area of this trapezoid ABCD will be equal to A plus B, that is the sum of its two parallel bases, times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. You can see here that it creates 90 degrees with the two parallel bases. So in conclusion, you can say that a trapezoid is a quadrilateral with one pair of parallel sides, and therefore any trapezoid equals to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2. And the height edge must create 90 degrees with those two parallel bases. So, in the first step, we'll define the relevant points to this question with letters. We'll define the center of this circle, this point is point O. Likewise, we define the point of tendency of tangent AB with this circle, this point is point E. We define the point of tendency of tangent DA with this circle, this point is point F. And finally, we define the point of tendency of tangent DC with this circle, this point is point G. In addition, we define the radius of this circle as X. In the next step, we'll join points O and E together by a straight line. By joining points O and E together by a straight line, what is the point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of this circle. This is equal to X according to our definition. So here we can implement rule 1. Repeat speaking on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle. AB is a tangent to this circle, is point M. OM is the radius of this circle, so this is equals to R. The radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can implement rule 1 in our drawing. Because in our drawing, we have the radius OE that equals to X. The radius OE is drawn to point E, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. If AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we'll join points O and F together by a straight line. OF is of course the radius of this circle, is equals to X, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we will join points O and G together by a straight line. OG is of course the radius of this circle, is equals to X, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral DGOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in the upper quadrant G or F, we have 4 integers, and according to rule 5, any quadrant that has 4 integers must be less than half integral, if not a square. So in order to quadrant DG or F, it's half integral, although it is a square. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle DG or F, side GO must be equal to the opposite side DF. But GO equals to X, therefore the opposite side DF must be also equal to X units in its length. Likewise, in the lower quadrilateral, FOEA, in the lower quadrilateral FOEA, we have 1, 2, 3 integers, and therefore this 4 pieces must be equal to 90 degrees in its size. So in quadrilateral FOEA, we have 4 integers, therefore we can relate to quadrilateral FOEA as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle FOEA, side OE must be equal to the opposite side FA. But EO is X, therefore the opposite side FA must be also equal to X units in its length. So in total, the length of side DA of trapezoid ABCD equals to X plus X, that is 2X. So this is side AD of trapezoid ABCD. This is equals to 2X units in its length. We define the length of side DC of trapezoid ABCD as A. DC equals to A units in its length according to our definition. It is given as the question that side AB equals to 3 units in its length. AB equals to 3. And CB is the missing side, so we leave this it is. In the previous lecture, I already proved that in trapezoid ABCD, actually it is in any trapezoid, DC, DA, side DA plus the opposite side CB is equals to DC plus the opposite side AB. It is true according to rule 2. So we use it in this question. We will not repeat on the same proof. So in trapezoid ABCD, side DA plus the opposite side CB is equal to side DC plus the opposite side AB. It is true according to rule 2. And again, in trapezoid ABCD, side DA plus the opposite side CB equals to side DC plus the opposite side AB according to rule 2. DC equals to A units in its length according to our definition. Plus AB. AB equals to 3 units in its length according to what is given as the question. And it is equals to side DA. DA equals to 2x units in its length. Plus side CB. CB is the missing side, so we leave this it is. So in total, we should find out that (2x plus CB equals to A plus 3). Here we we subtract 2x from this equation, and we get that the missing side CB is equal to A plus 3 minus 2x units in its length. This is the missing side CB. This equals to A plus 3 minus 2x units in its length. In the next step, we will do a construction. That is to say, from point C, we will draw perpendicular on AB. Again, from point C, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we get the big quadrilateral DCMA. In the big quadrilateral DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total the must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in the big quadrilateral DCMA, we have 4 angles. And according to rule 5, we can relate to quadrilateral DCMA as a rectangle because it has 4 right angles. So as a norm, the big quadrilateral DCMA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side MA or AM. But DC equals to A, therefore the opposite side AM must be also equal to A units in its length. AM equals to A units in its length. Likewise, according to the same rule, the same rectangle DCMA, side DA must be equal to the opposite side CM, but DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. What is the length of the missing line segment MB? From the drawing it is very easy to see that MB in total equals to AB minus AM. So it is on. The missing line segment MB equals to AB minus AM. So MB in total equals to AB is 3. Minus AM. You just write down further that AM equals to A units in its length. So in total, MB equals to 3 minus A units in its length. In the next step, we'll copy the right big triangle CMB in a new page and we will implement to this big right triangle CMB the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle CMB, this is the coordinate from the original drawing. This is right triangle CMB. CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. So write it down. CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB equals to A plus 3 minus 2x, therefore CB squared equals to A plus 3 minus 2x squared. And it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared. Plus MB squared. MB is 3 minus 8, therefore MB squared is 3 minus 8 squared. So in total we should find out that A plus 3 minus 2x squared equals to 4x squared plus 3 minus 8 squared. So here we'll open the brackets on both sides of this equation and we get that, actually we'll open the brackets according to the algebraic identity that states that A minus B squared equals to A squared plus B squared minus 2 times A times B. According to the algebraic identity that I mentioned, A plus 3 minus 2A squared, A plus 3 minus 2x squared equals to A plus 3 squared plus 2x squared. 2x squared is 4x squared plus 2 times A plus 3 times 2x, and it is equals to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared minus 2 times 3 times 8, that is minus 6A. So we have here A plus 3 squared. So we'll open the brackets of this expression and we get that A plus 3 squared equals to A squared plus 3 squared, that is 9, plus 2 times A times 3, that is 6A, plus 4x squared, minus 2 times 2x is minus 4x, so in total this expression equals to minus 4x times A plus 3 equals to 4x squared plus 9 plus A squared minus 6A. We have A squared on both sides of this equation, so A squared will get cancelled. We have 9 on both sides of this equation, so 9 also gets cancelled. And we have 4x squared on both sides of this equation, so 4x squared also gets cancelled. So we cancel those two expressions. This side of the equation we left only with 6a minus 4x times A plus 3, while on the other side of the equation we left only with minus 6a. So in total we should find out that 6a minus 4x times a plus 3 equals to minus 6a. Here we get 6a and also 4x times a plus 3 simultaneously to this equation, and we get that in this side of the equation we have 6a plus 6a, that is 12a, and on the other side of the equation we have 4x times a plus 3. So today we found out that 12a equals to 4x times a plus 3. Here we will divide this equation by 4, and we get that 12a over 4 is 3a, and 4x over 4 is x, so in total this expression equals to x times a plus 3. So in total we found out that 3a equals to x times a plus 3. Here we divide this equation by a plus 3, and finally we get that x equals to 3a over a plus 3. And again we found out that x equals to 3a over a plus 3. In the next step, we'll find out there of this trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. So what is there of trapezoid ABCD? There trapezoid ABCD equals to the sum of its two parallel bases, that is actually DC plus AB, DC plus AB, times the height over 2. The height is CM because it's greater than 90 degrees with the two parallel bases. So CM is the height over 2. So in total we should find out that the area of trapezoid ABCD is equal to the sum of its two parallel bases, that is DC plus AB, times the height CM over 2. DC equals to A units in its length plus AB. AB equals to 3 units in its length according to what is given as the question, times the height CM. CM equals to 2x units in its length divided by 2. So in total we shall know that the area of trapezoid ABCD is equal to a plus 3 times 2x over 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. So if it's 2, we're left with a plus 3 times x. So in total, we should find out that the area of trapezoid ABCD is equal to a plus 3 times x square units in its size. But it is given as the question that the area of trapezoid ABCD is equal to 3 units in its length. So we can substitute the area of trapezoid ABCD by 3. And we get that 3 equals to a plus 3 times x. 3 equals to a plus 3 times x. But we have already found out that x equals to 3a over a plus 3, so we can substitute x this equation by 3a over a plus 3. We do it now, we get that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. So today we found out that 3 equals to a plus 3 times 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 will get cancelled, and we're left only with 3 equals to 3a. Here we divide this equation by 3, and we get that a equals to 3 over 3, that is 1. So if you found out that a equals to 1 unit in its length. We have already found out that x equals to 3a over a plus 3. We just right now found out that a equals to 1. So we can substitute a in this equation by 1. We do it now and we get that x equals to 3a. 3a is 3 times 1, that is 3, over a plus 3. A plus 3 is 1 plus 3. That is 4. So in total we found out that the radius of the circle x equals to 3/4 units in its length. The radius of this circle that is described by trapezoid ABCD, the radius x equals to 3/4 units in its length. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, if you found out that the area of the circle, that is the area that we are looking for in this question, it is equal to either 9 pi over 16 square units in size, so in terms of numbers, it is equal to 1.767 square units in size. And that is the answer to the second question. Repeat again. I actually found out that the area that we are looking for in this question, that is the area of this circle, equals to either 9 pi over 16 square units in its size. In terms of numbers, the area of this circle equals to 1.767 square units in its size. So we finish with the the second question. In the next step, we summarize the lecture. We start with the first question, of course. Our task in the first question is to find out the size of this angle A and Q is equals to x. We have to find out the value of this angle x. So in the drawing we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. In addition, we know that OS equals to SB. Inside this semicircle we have this square PQSO. And again, our task is to find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside the square are right angles. So all those four angles are right angles in square PQSO. In addition, we know that all the sides of a square are equal to each other. So in square PQSO, side QS equals to side SO. QS equals to SO. But it is given as an equation that SB equals to SO. SB equals to SO, and in square PQSO, QS equals to OS. So from this equation, QS equals to OS equals to SB, we derive that QS equals to SB. QS equals to SB. In the next step, we did a construction, that is to say, we joined points B and Q together by a straight line. Then we extended the straight line BQ by a straight line until it touches the circle, the semicircle. We define the touching point of the extended side BQ with this semicircle. This point is point M. And we extended the straight line BQ by a straight line. When you extend the straight line by a straight line, the result is a straight line. Therefore, BN is a straight line. By doing this construction, we can do like SQSB. But before that, we know that AB is the diameter of this semicircle. AB is the diameter, it is absolutely a straight line. So if we focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. In this case, it means that the sum of the angles on the upper side of the straight line AB at point S must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of AB at point S? We have this angle that is a right angle, plus this missing angle, and total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So by doing this construction, we're going to do the right triangle QSB. In the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes. Okay? According to the rule that in front of equal sides in the triangle, there are equal angles. So those two angles must be equal to each other. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other. And we know that the sum of the angles in a triangle is equal to 180 degrees. And therefore the sum of the angles in triangle QSB must be equal to 180 degrees. Which angles we have in the right triangle QSB? We have y plus y, that is 2y plus 90 degrees. In total it must be equal to 180 degrees according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So again, the sum of the angles on the right triangle QSB must be equal to 180 degrees. That is to say, 2y plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation. If I found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2. If I found out that the missing angle y equals to 90 degrees over 2, that is 45 degrees. So here this is the missing angle y that is equal to 45 degrees in size. And this is also the missing angle y that is equal to 45 degrees in its size. I've already proved that MB is a straight line. NB is a straight line, so if we focus on the left side of the straight line NB at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line NB at point Q? We have this angle that is 45 degrees, plus this angle that is 90 degrees, plus this missing angle NQP. In total, they must be equal to 180 degrees according to rule 3. Repeat again. and B, the sum of the angles of the straight line and B at point Q must be equal to 180 degrees according to rule 3. So which angles we have at the left side of NB at point Q? We have 45 degrees plus 90 degrees plus the missing angle NQP. In total, they must be equal to 180 degrees according to rule 3. 45 degrees plus 90 degrees is 135 degrees, so 135 degrees plus the size of the missing angle NQP. In total, they must be equal to 180 degrees. Here we subtracted 135 degrees from this equation. If I found out that the missing angle NQP equals to 180 degrees minus 135 degrees, it's 45 degrees. This is the missing angle NQP that is equals to 45 degrees in its size. In the next step, we join points N and M together by a straight line, and we also joined points N and A together by a straight line. By joining points N and A, we get it peripheral and A and B. This is peripheral A and B that subtend on the diameter of this semicircle. This is actually called AB. And according to rule 7, any peripheral that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. And because of the fact that peripheral A and B subtend on AB, that is the diameter of the circle, of the semicircle, it must be equal to 90 degrees in its size. According to rule 7. Those two angles, they are both subtend on chord AN. This is angle ABN, angle AB, peripheral angle ABN is definitely subtend on chord AN. Likewise, this is peripheral angle AMN, peripheral angle AMN subtend on the same chord called AN. And because of the fact that those two peripheral angles subtend on the same chord called AN, they must be equal to each other in their sizes. But this peripheral angle ABN equals to 45 degrees in size, therefore peripheral angle AMN that subtend on the same chord called AN must be also equal to 45 degrees in its size according to rule 16. So peripheral angle AMN equals to 45 degrees in its size. In the big triangle A and B, the big right triangle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees according to rule 7. Therefore, this missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the big right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths. That is to say, in the right triangle A and B, side AN must be equal to side NB. According to the rule that in front of equal angles in the triangle, they are equal sides. So AN equals to NB. AN equals to NB, it means that the right triangle A and B is also an isosceles triangle. Triangle A and B is an isosceles triangle. AB is the base of the isosceles triangle, triangle A and B. Again, AB, side AB is the base of the isosceles triangle, triangle A and B. But AB is also the diameter of this semicircle. So AB is simultaneously the base of the isosceles triangle, triangle A and B. And AB is also the diameter of this semicircle. So here, you can implement rule 24. In our drawing, according to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. We can implement rule 24 in our drawing. Because in our drawing, we have the isosceles triangle, triangle A and B. The base of the isosceles triangle, triangle A and B is AB. According to rule 24, the perpendicular from point N to the base AB bisect the base AB. AB is the base of the isosceles triangle, triangle A and B, and A and B is also the diameter of this semicircle. So AB is a diameter, is twice as long as the radius. If the radius of this circle is R, then the diameter AB must be equal to 2R. So AB equals to 2R. And if the perpendicular from point N bisects the diameter AB, means that it divides it into two halves. Each half must be equal to AB over 2, that is 2R over 2. 2R over 2 is R, so the first half is R, and the second half is also R. The perpendicular to the base must touch the base at its midpoint. So the perpendicular from point N must touch the diameter AB at its midpoint. What is the midpoint of any diameter? The midpoint of any diameter is the center of the circle or the center of the semicircle. In this case, it's the center of the semicircle, that is at point O. That is to say, for the perpendicular from point N must touch side AB at point O, that is the center of the diameter. So NO bisect the diameter AB into two halves. Each half equals to the radius of the circle. So NO is the perpendicular, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. And each half of the diameter AB equals to half. The first half is half and the second half is also half. We know that the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. Those two angles are defined as corresponding angles and are located between the parallels PQ and OS, and therefore they must be equal to each other. But this angle is 90 degrees, and therefore this angle must be also equal to 90 degrees in its size, according to the rule that corresponding angles between the parallel lines are equal to each other. So, in the next step, I prove that quadrilateral NMQP, this is quadrilateral NMQP, that quadrilateral NMQP is a cyclic quadrilateral. That is to say, quadrilateral NMQP can be blocked by a circle, can be inscribed by a circle. First of all, what is the meaning of the sentence that a quadrilateral is inscribed by a circle? This is quadrilateral ABCD. Quadrilateral ABCD is inscribed by this circle. Why quadrilateral ABCD is inscribed by this circle? Because of the fact that all the four vertices of quadrilateral ABCD lie on the circle. This is vertex A that lie on the circle, vertex B lie on the circle, vertex C lie on the circle, and the vertex D also lie on the circle. So a quadrilateral that is inscribed by a circle only and only if all the four vertices lie on the circle. Okay, so we have to prove that quadrilateral NMQP is a cyclic quadrilateral, can be inscribed by a circle. That is to say, all the four vertices NMQP of quadrilateral NMQP lie on a circle. So first of all, we know that those two angles, they are both equal to 45 degrees in their sizes, and they both lie on the base NP. Angle PMN lie on the base NP, and angle NPQ and QP also lie on the same base NP, and therefore those two angles are fit to a circle. That is to say, those two angles can be inscribed by a circle. Exactly according to Rule 16, that it said that if two peripheral angles subtend on the same chord, they are equal to each other. Those two peripheral angles subtend on the same base NP, and therefore they are equal to each other. Each of them is equal to 45 degrees. And this rule is applied to peripheral angles that, of course, subtended that are in the circle. And therefore, those two angles, they can be inscribed by a circle. That is to say, we have here, this is peripheral angle NQP, that equals to 45 degrees in its size, and it's subtend on chord NP. Likewise, this is peripheral angle NMP. Peripheral angle NMP also equals to 45 degrees in size, and it's subtend on the same chord called NP. So you can see that those two peripheral angles that are equal to each other, they subtend on the same chord called NP, and therefore they can be inscribed by a circle. but all the other angles so those two angles, they are both lie on the circle. This is peripheral angle NQP, the vertex Q lie on the circle, and this is peripheral angle PMN, the vertex M of peripheral angle PMN also lie on the circle. What happening about all the angles that don't lie on the circle? If angle PLN lie outside this circle, and it subtend on the same chord called PN. Angle PLN that lie outside this circle, the vertex L is outside this circle, and angle PLN subtend on chord PN. But it is equal to 39 degrees in size. So you can say, you can also try and build angles that lie outside this circle and subtend on chord PN. All the angles that lie outside this circle and subtend on chord PN will be less than 45 degrees. Like this angle that is 39 degrees in its size. So all the angles that subtend on chord PN and lie outside this circle, they are less than 45 degrees. While all the angles that subtend on the same chord PN and they are located inside the circle, that is to say, their vertices are inside this circle, like this angle PON, its vertex A is inside the circle. But it is equal to 85 degrees in its size. We can try to build any angle that is inside this circle and subtend on chord PN. All the angles will be bigger than 45 degrees. So all the angles that lie outside this circle and subtend on chord PN will be less than 45 degrees, while all the angles that lie inside this circle and subtend on the same chord PN will be bigger than 45 degrees. Therefore, we can conclude that only the angles that lie on the circle itself and subtend on PN, on chord PN, will be equal to 45 degrees. All the other angles, either they will be less than 45 degrees or bigger than 45 degrees. So all the angles that would be equal to 45 degrees and subtend on chord PN will be on the circle itself. The vertices will be on the circle itself. Therefore, first of all, we will take angle P, angle NQP, that is also triangle NQP. I copy this triangle NQP in a new page. This is angle NQP. This is angle NQP. Angle NQP is also it is located inside triangle NQP. So cover this triangle NQP here with angle NQP. This is equal to 45 degrees in its size. And we have the rule that all the triangles in the world can be inscribed by a circle. Or all the triangles in the world are cyclic triangles. Therefore, this is triangle NQP that we can definitely block by this circle. So in triangle NQP, we have angle NQP that subtend on chord NP, and the size of angle NQP is 45 degrees. Now, we rotated angle NQP along this circle without changing its size. On the axis PN, the axis PN is not moving, only the vertex is moving along this circle without changing the size of the circle, that is 45 degrees. By rotating the angle along this circle, we will create infinite angles that all of them will be equal to 45 degrees in their sizes, and they are all located on code Pn because we will not move code Pn. Only the vertex is moving along this circle. Out of the infinite angles, that each of them is equal to 45 degrees, and they are all located on chord, and they are all subtended on chord Pn. One of them will be angle PMN. The size of angle PMN is 45 degrees, and it is also subtended on chord Pn. Exactly like those two angles, this is 45 angle PMN, that is equal to 45 degrees in size, and it's subtended on the base NP, and this is angle PQN, that is also equal to 45 degrees in size, and it's subtended on the same base NP. But here we succeeded to block those two peripheral angles inside this circle. In the next step, we will join points M and Q. In this way, created quadrilateral NMQP that is definitely blocked by this circle. Quadrilateral NMQP is inscribed by this circle. Why? Because of the fact that all of its four vertices, they all lie on the circle itself. This is vertex M that lie on this circle. This is vertex M that is definitely lie on this circle. This is vertex Q that lie on this circle, and this is vertex P that lie on this circle. So in this way, prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, it can be blocked by a circle. You can see here that quadrilateral NMQP is blocked by this circle. So we can write down actually that quadrilateral PMQN is a cyclic quadrilateral. That is to say, it can be inscribed by a circle, it can be blocked by a circle, exactly like represented to you, that it is definitely can be inscribed by a circle. But we have the rule that states that the sum of two opposite angles in a cyclic quadrilateral is equal to 180 degrees. And again, we have the rule that says that the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. First of all, we blocked this quadrilateral NMPQ by a circle. And I want to show to you that quadrilateral NMQP is a cyclic quadrilateral. So we blocked quadrilateral NMQP by this red circle. You can see that quadrilateral NMQP is definitely blocked by this red circle because of the fact that all of its four vertices lie on the red circle. So quadrilateral NMQP is inscribed by this red circle. And according to the rule that I presented to you, the sum of those two opposite angles in quadrilateral NMQP must be equal to 180 degrees. So this is angle NPQ is equal to 90 degrees in its size, plus this opposite angle, this is angle NMQ, in total must be equal to 180 degrees according to the rule that I presented to you. So in the cyclic quadrilateral PMQN, angle NPQ plus the opposite angle NMQ, in total they must be equal to 180 degrees according to the rule that I presented to you. Angle NPQ equals to 90 degrees in size, angle NMQ in total equals to 45 plus x degrees in its size. And again, angle NPQ equals to 90 degrees in size, and angle NMQ, the opposite angle NMQ, equals to 45 degrees plus x degrees in its size. 90 degrees plus 45 degrees is 135 degrees, so 135 degrees plus x equals to 180 degrees. Here we subtract 135 degrees from this equation, and finally found out that the missing angle, x, that this is the angle that we're looking for in this equation, equals to 180 degrees minus 135 degrees is 45 degrees. So here this is the missing angle x, that is also equals to angle AMQ, that is equals to 45 degrees in its size. Repeat again, we actually found out that the missing angle AMQ, that is equals to x, is equal to 45 degrees in its size. And that is the answer to the first question. In the next step, I presented to you the second question, and we solved the second question of this lecture. In the second question of this lecture, our task is to find out the area of this circle that is described by trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. In the drawing we have quadrilateral ABCD, and because of the fact that in quadrilateral ABCD side DC is parallel to the opposite side AB, quadrilateral ABCD is defined as a trapezoid because it has one pair of parallel sides. So the two parallel sides, that is to say DC and AB, are defined as the bases of this trapezoid ABCD. So we define the base, the length of base DC as A, and the length of the base AB as B. Then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. So, in conclusion, we can say that a trapezoid is a quadrilateral with one pair of parallel sides, and any trapezoid equals to the sum of its two parallel bases, that is to say it is A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So in the drawing, we have a circle that is described by trapezoid ABCD. Those two angles are both right angles. In addition, we know that this is side AB of trapezoid ABCD, that is equals to 3 units in its length, and the area of this trapezoid ABCD is equal to 3 square units in its size. Okay. The area of trapezoid ABCD equals to 3 square units in its size. Again, our task is to find out the area of this circle that is described by trapezoid ABCD. So first of all, we define the relevant points of this question with letters. We define the center of this circle. This point is point O. We define the center of this circle. This point is point O. We define the point of tendency with this circle. This point is point G. We define the point of tendency of tangent DA with this circle. This point is point F. And finally, we define the point of tendency of tangent AB with this circle. This point is point E. We also define the radius of this circle as X. Radius equals to X. In the next step, we join points O and D together by straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore OE is the radius of the circle, that is equals to X. The radius OE that is equal to X, the radius OE is drawn to point E, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. If AB is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by straight line. OF is the radius of this circle, that is equal to X. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and G together by straight line. OG is the radius of this circle, that is equals to X. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in quadrilateral DGOF, we have 1, 2 for rectangles. The sum of rectangles is 270 degrees, so 270 degrees plus the size of this 4th angle In total, they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this four-piece angle must be equal to 90 degrees in its size. So inside quadrilateral DGOF, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral DGOF as a rectangle because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So in rectangle DGOF, side GO must be equal to the opposite side DF. But GO is x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrilateral OFAE, we have 1, 2, 3 rectangles. And therefore this four-piece angle must be equal to 90 degrees in its size. In quadrilateral FOEA, we have 4 rectangles. Therefore we can relate to quadrilateral FOEA as a rectangle. But we know that the opposite sides of a rectangle are equal to each other. So rectangle FOEA, OE equals to side OE equals to the opposite side FA. But OE is x, therefore the opposite side FA must be also equal to x units in its length. So in total, the length of side DA of trapezoid ABCD equals to x plus x, that is 2x. We define the length of side DC of trapezoid ABCD is A. We know that AB equals to 3 units in its length according to what is given in the question. CB is the only missing side. We have already proved that in any trapezoid, DC plus the opposite side AB equals to DA plus the opposite side CB. It is true according to rule 2. So trapezoid ABCD, DA plus the opposite side DB equals to DC plus the opposite side AB according to rule 2. DA equals to A, DA equals to 2x, CB is the missing side, so it is. And it is equals to DC, that is A, plus AB, that is 3. So in total, if you found out that according to rule 2, 2x plus CB equals to A plus 3. Here we subtracted 2x from this equation, and finally found out that the missing side CB equals to A plus 3 minus 2x units in its length. This is the missing side CB. The missing side CB equals to A plus 3 minus 2x units in its length. In the next step, we did the construction, that is to say, from point C we drew perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point N. By doing this construction, we get quadrilateral DCMA. In quadrilateral DCMA, we have 2 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this four-piece angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this four-piece angle must be equal to 90 degrees in its size. So in quadrilateral CDAM we have 4 rectangles, and therefore according to rule 5, we can relate quadrilateral DCAM as a rectangle because it has 4 rectangles. But you also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle CDAM, side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. Likewise, according to the same rule, in the same rectangle CDAM, side CD must be equal to the opposite side AM. But CD equals to A, therefore the opposite side AM must be also equal to A units in its length. What is the length of the missing line segment MB? MB equals to AB minus AM. AB equals to AB minus AM. So MB equals to AB, that is 3, minus AM, that is A. So in total, MB equals to 3 minus A units in its length. In the next step, I complete the right angle CMB in a new page, and implement the Pythagoras theorem on this right angle CMB. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle CMB to the limit of the original domain. This right angle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB is a plus 3 minus 2x, therefore CB squared is a plus 3 minus 2x squared, and it is equals to CM squared. Equals to CM squared. CM is 2x, therefore CM is 2x squared, that is 4x squared, plus MB squared. MB is 3 minus 8, therefore MB squared is 3 minus 8 squared. So in total we should find out that a plus 3 minus 2x squared equals to 4x squared plus 3 minus 8 squared. We open the brackets on both sides of this equation according to the algebraic identity that states that a minus b squared equals to a squared plus b squared minus 2 times a times b. According to the algebraic identity that I mentioned, a plus 3 minus 2x squared equals to a plus 3 squared plus 2x squared, that is 4x squared, minus 2 times a plus 3 minus 2x. On the other side of the equation we have 4x squared plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared minus 2 times 3 times 8, that is minus 6a. We have here a plus 3 squared, so we open the brackets here, and we found out that a plus 3 squared equals to a squared plus 3 squared, that is 9, plus 2 times a times 3, that is 6a, plus 4x squared minus 2 times 2x is minus 4x, so in total this expression equals to minus 4x times a plus 3, and it is equals to 4x squared plus 9 plus a squared minus 6a. We have a squared on both sides of this equation, so a squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled. And we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. And we left only this side of the equation with 6a minus 4x times a plus 3. While on the other side of the equation we left only with minus 6a. And again, in total, we actually found out that 6a minus 4x times a plus 3 equals to minus 6a. Here we added 6a and also 4x times a plus 3 simultaneously to this equation, and finally found out that 6a plus 6a is 12a equals to 4x times a plus 3. Here we divided this equation by 4 and finally found out that 12a over 4 is 3a and 4x over 4 is x, so in total this expression equals to x times 3, x times a plus 3. So in total we found out that 3a equals to x times a plus 3. Here we divided this equation by a plus 3 and finally found out that x equals to 3a over a plus 3. In the next step we calculated the area of this trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. So according to the formula, the area of trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually DC plus AB, times the height CM over 2. And again, the area of trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually DC plus AB, times the height CM over 2. DC is A, AB is 3, CM is 2x divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we have only with a plus 3 times x. So total we should find out that the area of trapezoid ABCD equals to a plus 3 times x, square units in its size. This gives us the question that the area of this trapezoid ABCD equals to 3 square units in its size. So we substitute the area of trapezoid ABCD by 3, and we found out actually that 3 equals to a plus 3 times x. Here we divided, but we already found out that x equals to 3a over a plus 3, so we can substitute x here by 3a over a plus 3. We did it, and we found out that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. We have a plus 3 the numerator and a plus 3 the denominator, so 3 equals to 3a. So a plus 3 get cancelled, and left only with 3 equals to 3a. Here we divided this equation by 3 and finally found out that a equals to 3 over 3, that is 1. So a equals to 1 unit in its length. A equals to 1 unit in its length, and we only found out that x equals to 3a over a plus 3. So we can substitute a, this equation, by 1, because a equals to 1. We did it, and we found out that x equals to 3a. 3a is 3 times 1, that is 3, over a plus 3. A plus 3 is 1 plus 3, that is 4. So in total we found out that the radius x of this circle equals to 3/4 units in its length. Our test is to find out the area of this circle. Actually we know that the area of any circle equals to pi times the radius of the circle squared. and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total we found out that the area of our circle equals to pi x squared. X is 3/4, therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total we found out that the area of our circle equals to either 9 pi over 16 square units in size, or in terms of numbers, the area of our circle is equal to 1.767 square units in size. Repeat again, we should found out that the area of this circle, that is the area that we are looking for in this question, is equals to either 9 pi over 16 square units in size, or in terms of numbers, the area of this circle equals to 1.767 square units in size. Okay? Thank you very much.